All right, welcome back to Mechanical Systems Design. In this video, we'll discuss detailed stress analysis, or mostly finite element analysis in design. And before we start, you should read the topic reading, or a lot of this won't make sense. And then you should watch the FEA tutorial videos. We have a click-by-click walkthrough of how to perform finite element analysis and get results for stress and displacement in both SOLIDWORKS and Fusion 360. And we'll build on that in this video. All right, so just a very high level overview. Finite element analysis is a powerful tool for understanding what will happen with your mechanical system. And it is a good complement to simple model analysis. Its strengths are that it's more accurate and general. So you could throw any shape in there you like and get a useful result. But it's also slower, both in the time it takes you to model your part and then run the analysis. And it's not directly invertible. That is to say, it's hard to take that stress plot and turn it directly into information about how to improve your design. The way that really happens is you map that information from FEA back onto simple models that you have in your mind of your part. And that's how you actually figure out how to improve it and come up with ideas about how to make a better design. So we're going to spend most of our time in this video going through some examples from the Vice script, and we won't have any exercises. And we'll start with link one. So we learned how to generate a free body diagram of link one in the free body diagrams video. We did simple model analysis of the stress in link one in our last video. And here we'll do FEA. And the big questions that we should have as we set up a finite element analysis problem are what kind of fixtures am I going to use? What kind of loads will I apply? And then what am I interested in learning from FEA? And how will these choices I make affect that, that interpretation? So I'm going to pop over to SOLIDWORKS now, where I've got this part. So the very simplest way to perform FEA of this part would be, well, to first create a static study and then simply fix the inside of one of the holes and apply a force on the inside of the other hole and put that in the direction we care about. Let's give it a meaningful number, 100 pounds force, and then run the study. So this, we have a fixture, we have a load, we will get an answer. And it runs very fast. And that's the strength of this very, very simple setup approach. You can get something quickly. Now, we'll see that there are some problems, and we'll come back to those in a moment. But let's first notice what's good about this. In the areas far away from our constraints and loads, we have a pretty good stress analysis result. As we would expect from simple axial compression, the stress is distributed very evenly. It doesn't say get higher on the edges or something like that. And if we were to do back of envelope analysis of the stress in this part, it would match finite element analysis quite closely. So that's good. And so many times you can get a useful understanding of what's happening in the middle of your part without a whole lot of complex constraints and loads and assemblies and so on around the edges that take a lot of time. But we do see there are some issues. If we're interested in understanding the stress near these holes, then there are some evident problems. We've got very asymmetric deformation, which is a warning to us because we expect it to be symmetric. And this hole is kind of collapsing. So why is that happening? Well, it's because of the way we chose to apply that force. We are applying a force in that direction on the entire internal surface of that hole. And that means that part of the hole has the pin pulling away from it, and it's actually getting a force on it that's moving in that direction, which wouldn't happen in the real system. So one way to handle this is to go back to our model and to create a split line. So we're going to create a new sketch, and we'll sketch a line from the top of the circle down to the bottom of the circle. And that's all we need from our sketch, just a line that intersects this cylinder. Then we will go to Features, Curves, Split Line, and we'll select the sketch we just made, and then in internal surface of that hole, say OK. And you'll see that now, when I hover, they're actually two separate surfaces. And that's going to allow me to apply the force in our static simulation just to one side. Got an issue here because that original surface is gone. So I'm going to edit the definition and then pick just the inside surface that would be under compression from that force. We'll say OK, and we can run the study again. And once again, it runs very quickly. And we can see that that outer ring is no longer doing this weird squishing, which is good. That's an improvement. However, the inside surface has a stress pattern that we don't quite expect. You see that there's high stress at maybe 10 and 2 instead of right at 12 o'clock, where you might expect it if you have a round pin pushing into a round hole. So it turns out there's an even better way of doing this. That happens because the force is evenly distributed around that surface. And so there's a lot of force on these edges that wouldn't see much force in real life. So what we can do is apply a bearing load. But before we do that, we'll have to create a little bit more reference geometry again. And in this case, we're going to sketch a line that goes from the center of this circle. Let's see, center of this circle, all the way to the center of this circle. And that's all we'll need from the sketch. Also, we really want to point at the center of each of those circles. And we'll then go to Features and create reference geometry. And we want a coordinate system that our bearing load will use to know how much force to put where. So first we need a point. We'll select that. And then actually these default directions look pretty good. We'll want to force in the positive x direction there. So let's say OK. And now let's create another one over for our second hole coordinate system. We'll select that point and the default axes look pretty good. Okay. And I'm going to hide this sketch now so that we're not looking at the analysis. All right, so if we go over to our static analysis again, let's suppress this force that was on the half of the circle and apply a new load, and we'll select the bearing load. So we want to pick that same surface, and we'll select the coordinate axis we just made. And English units, 100 pounds force again, reverse the direction so it shows up. And then down here, you can see there are some choices we can make about the distribution. And we're going to use the sinusoidal distribution. And that's going to set how much force occurs at each point in that arc. So we say OK, and we run the study again. We can see it runs very fast again, because all we've done is changed what forces are going on those nodes. The complexity hasn't increased, really. And now we're getting a stress pattern in this hole that looks a little bit more like what we'd expect. And that's good. But we still have this issue of the asymmetry. And the reason that we're not getting a lot of stress concentrated in the middle of this hole is because we have fixed that surface. It's very easy to fix something, but it's quite an approximation of what's going to happen in the real system. It really is a little different from what would happen if you put a pin in this hole and then it reacted out of force. So instead, why don't we apply a bearing force on the inside of this hole as well. So we'll come up to this fixture and suppress it, and then we'll create another bearing load. I'm going to put it here. We need this coordinate axis. Positive x direction is good. English units. an equal and opposite force, same distribution. We're okay with that. Now, if I try to run this, I'm going to get an error. And it's going to say there are no restraints defined. So in our perfect hand analysis world, equal and opposite forces exactly cancel, nothing happens. But since this is a numerical analysis, little tiny differences due to numerical error would cause there to be a slight force or moment imbalance, and this thing would fly off to infinity. So we do need to add some kind of constraint. And a little quick hacky thing we can do here is to fix just one little line somewhere, because we know these forces are really, really close to equal and opposite. So we pick this little edge and fix it. That'll allow us to react out the tiny forces that will be needed to keep it from spinning or flying off to infinity. And then we can run the study. In more complicated problems, or where you don't have quite the same level of accuracy, you may need to define a plane and keep that from rotating or something like that. Oh, we're getting excessive displacements. That's because this whole thing is just twisting a little bit. If you ever get those excessive displacements, you don't probably want to use the large displacement option. It takes a long time. It's a big nonlinear problem. So you either want to just keep it with the small displacement solver and see what you got, or make some changes to how you set the problem up. So we'll say no. And yeah, you can see that it's complaining because this whole thing has rotated a little bit, but that hasn't actually affected the pattern of stress. And now we have a pretty darn symmetric pattern of stress with peaks in the center of these holes. And everything looks about like we might expect. And just to get a sense of this, let's see what that peak stress value is in PSI so we can compare it. And a little bit under 4,000 PSI. Okay, great. So we've improved iteratively the way we handle the forces from the pegs on this link, but it's still an abstract representation of the real peg. And if we want to get really good accuracy for the stress around these contact points, we need to do is actually model the peg itself as well, since it will be another deformable body in the simulation. And we can do that with an assembly analysis. So I'm going to pull that up. All right, so here we have an assembly we've created that includes our link and also some models of the pins that will go in those holes. And an assembly stress analysis will work just the same as the component analysis with just a few new options. So we'll create a new study, static. And this time you can see that under connections, we have component contacts. And there's a global contact that means all the parts are included in it. It says bonded. Bonded means that the parts will be treated as if they're all one continuous component. And that's not what we want. We want the peg to be able to move away from that surface if it would be in tension. So we're going to right click here and edit the definition. And we're going to select no penetration. No penetration means that if two parts are incident upon each other, there will be a reaction force and they will not be able to pass through each other like ghosts. That's what allow penetration means. Bonded means they're glued together so they can't pull away from each other. No penetration means they can pull away but can't pass through each other. And let's add a little bit of friction to try to capture that. These two parts will have a little bit of friction as they try to slide past each other. Okay. Now for fixtures, we can fix our pin, and that will be okay because we're not interested in the stress around this fixed point on the pig. We're interested in the stress on the link. So moving that abstraction away from the thing that we care about will make the results we care about more accurate. And then we can apply our force, again, to these outer faces of this peg. And we want those in a selected direction, so to be compressive. And we'd like it to be the total force in English units, 100 pounds force, and the opposite direction, please. All right. So we've got it all set up, and we can now run the study. And what we'll see is these assembly analyses tend to take a little bit longer to run, and that's what you pay for the higher accuracy. And part of the thing that makes it take longer to run is that it has to resolve how much these surfaces slide past each other under friction. So I'm going to pause the recording for a moment and come back when it finishes. All right, so that took about a little less than 1 minute to run. And you can see we have slightly different results than when we applied those bearing loads. To get a closer look at what's happening, let's go back to our model, and we're going to hide our shafts so that we can see what's happening on the inside of those holes better. And let's see. Now the stress isn't evenly distributed across that edge, but it is on these edges on either face of the link. And what's happening is that that shaft is bending a little bit, and so it's pressing more on these outer edges and generating a higher stress. And if we change this over to PSI for comparison, let's see, we've got more like 7,000 PSI. So that's a substantial increase in the stress. So as we have moved through this process, the amount of time it's taken us to both set up the problem and run it in FEA has increased, and so has the accuracy of our estimates of stress. So what we can see is running FEA on doing a quick up FEA on a simplified version of your candidate design early in the process will help you to see big patterns of stress in the main component and help you to make some good decisions early on to get the shape set right. And then you can use this more refined stress analysis and finite element analysis, especially assembly analysis, very late in the process when you're working fine-tuning little details of how, say, two components connect together. And I'll show you one more example of this through link 2. Let me pull that up. All right, so here we have the setup for analyzing link 2. And you can see it's an assembly analysis, and it's a little more complicated. So how did we get here? Well, if you think about maybe the very simplest ways to try to set this problem up, one might be to fix this hole, apply a force along the line of action of link 1 at this hole on link 2, and apply this force from the hand along the handle. But the problem with that is that by fixing this hole, we allow it to create a reaction moment. And we know that that's not really what's going to happen in the real system, because that pin would just be able to rotate with a little bit of friction, but more or less freely in the hole. And what we would find if we ran this simulation is that we'd get a big reaction moment at this hole, which is inaccurate. Okay, so maybe instead we should put a bearing fixture, which is what we have here. And that's good. But if we have the bearing fixture with this force and that force, there's nothing left to react out any tendency to spin around that bearing. And unless we get these forces exactly right, and they're never exactly right, as we talked about a minute ago in these numerical analyses, there's going to be a tendency to spin. And it turns out actually to be pretty tricky to hand calculate these forces to be so well balanced that our little trick of fixing an edge doesn't create some weird stuff. Okay, so we need something that can react out little numerical imperfections in this hand force. What about a bearing load here as well in link 2? Well, that would allow our analysis to solve, but if we put a bearing fixture in that hole, now it can create a reaction force in any direction. And we know that the reaction force here is only allowed to be in one direction, which is along the line of this link. And we discovered that in our free body diagram analysis before. So what we have here is we've modeled link 1 and these shafts, and we've hinged this top link with a bearing support. And down here we have the pin going through link 2, and we'll be actually analyzing that in FEA. And this means that the reaction force at this hole will naturally result to be along the line of action of the first link. And we have our nice bearing down here and our assumed external load from the hand here. So everything will be copacetic. So it'll take a little longer to run, but we'll get more accurate. So, so how do we set this up? Well, one of the things we'll see first is that under parts, we have a bunch of components now. That's these two shafts, the two links, and link 2. And some of them have different color here, and that's because they've been set to rigid. So if you right click on something here, one of the options is make rigid. And that simplifies the analysis because we're not really so interested in the stress inside link 1 and these shafts. For our purposes here, our intention is to understand the stress in link 2. So if we make everything but link 2 rigid, everything will compute a little faster. All right. The other thing to notice is the component contacts. So once again, we've got our global contact of no penetration, but here we've created a special contact. We've bonded some of these components together. So we've taken the 2 link 1s and the 2 shafts, and we've bonded it all together. So now it's one big rigid thing that makes the computation go a little faster as well. All right, these are our bearing supports. As we discussed earlier, they just mean that the circular cylindrical surface can rotate freely, but it can't translate freely. And there are some other little options for allowing it to rotate or in different, perhaps stiffness in different directions, but here we're just using it as basically a hinge. And then we have our external force, that's that hand force. So if we run this, it takes about 2 minutes to run. We get the following pattern of stress. Notice there's no pattern on link 1 or the shafts because we've set those as rigid and we don't know anything about what's going on inside them. And this looks reasonable. So let me go back to the model and we'll hide our links, our link 1 and shafts, so that we can see what's going on inside link 2 a little bit better. All right, so let's interpret what we have going on here. And we'll start with this part of the handle, which we analyzed a few days ago. So there's very little stress at the end, and which is what we expect because we previously thought of this as a cantilever bending problem. And this is the free end of the beam where there's very little stress because there's very little moment. Over on this end, we're seeing brighter colors, more stress. And that's what you expect with a cantilever bending problem. The moment is highest here as we calculated, and so the stress should be highest as well. We also see that the stress towards the middle, the centroid, is very low, which is what we expect with bending, and it's higher on those outer surfaces. So this portion is looking as we expected, cantilever bending. What's going on with the hole here? Well, you can see there's a big contact stress, more or less centered on the back face of that hole, just like we saw in the link 1 example. So things are looking pretty good there. Now this last section looks a little bit different maybe from things that we're accustomed to looking at. We see that as we move across the cross section, the stress is changing. And if that's happening as you move across the cross section, that's a sure sign that there is bending or torsion, in this case bending. So we have some bending, but the stress is not lowest right in the middle, and it's really high on one face and a bit lower on the other face. So what's going on? Well, it turns out this is not pure bending. This is going to be a combined loading situation. So we have both bending, and it will turn out, and we know we have bending because if we cut at this cross section, we had bending on this side, equal and opposite bending on this side. Well, something else is happening, which is that part of the force from link 1 onto link 2 is compressing this section. So we have bending combined with compression. And if you think through it carefully, you'll see that the bending we have here is going to tend to put the top here in compression. So we have some compression due to the bending plus axial compression. Well, those things add and you get even higher stress. On the bottom, the bending stress would tend to result in a tensile stress down at the bottom. Well, that cancels some of the compressive uh, axial compression stress. And so you get lower stress down at the bottom. So you can see how these complicated patterns of color that we generate with finite element analysis are really difficult to understand unless we map it back to simple models that we do understand. And those will tell us why we're seeing what we're seeing, and they can give us some hints about what we could do to make the design better. All right, just a few little last thoughts. Okay, so just a few last thoughts to leave you with as you think about how to set up your finite element analysis problems. One of the critical choices is which component or piece of a component or assembly of components you include in your analysis, as always. And we saw that for analyzing link 2, it was actually easier to get an accurate result by doing an assembly analysis than it would have been to come up with some contrived way of trying to get that with just a single part. And all of the simple ways of analyzing the single part would have been qualitatively wrong. They would have given us really inaccurate results, inconsistent with our simple model. It is essential to get the loading right for your part. If your free body diagram is wrong, your finite element analysis can't be right because those applied loads will be wrong too. So there's no way around uh, really understanding the problem from an FBD and simple model stress perspective. Those are essential. When you set up the fixtures, you're either giving up on believing the stress results nearby, which is okay early on, or you're putting them on a thing that you don't care about, that you've added sort of as a sacrificial component in assembly, say. When you do an assembly analysis, make sure to use no penetration, use bonded. Things won't work out well. It'll be, uh, you'll get almost no benefit from the assembly in many cases. As you look at your results, if you see weird, quick changes in stress, try refining your mesh. And keep an eye on the meeting of those, the results of the stress plots. The color will automatically adjust given the stresses and may not always mean the same thing as you refine. If you run into any questions as you go, see the tip sheet. We've got lots of good little click-by-click guidelines. All right, so our next video will be on technical writing. Happy designing out there.